Welcome to our discussion on the dual head infiltrometer. Let me take just a minute before we get into that to introduce METR. METR has several locations throughout the world, but the main ones are at Pullman, Washington, and Munich, Germany. Both of those locations we do engineering and manufacturing. You have about 200 employees in Pullman, about 35 in Munich. And there are two main subdivisions in the company, METR Food and METR Environment. METR Food focuses mainly on instrumentation for food measurements. METR Environment does both above ground and below ground instrumentation for measuring environmental variables. In METR Environment, I've just shown a number of the instruments that we build. On the left is a particle size, automated particle size analyzer. Next thing over with the three prongs is a soil moisture sensor. Next one over is a matrix potential or soil suction sensor. The larger thing with the blue ring around it is a mini weather station that measures 12 variables. Next over with the black top is a data logger, solar powered data logger that has cell connections. And finally, on the right is our dew point potentiometer that measures soil suction over the whole range. So that gives you a feeling. Those aren't all of the instruments, but a few of them that we do. Now, the one that we want to talk about today specifically is the automated dual head infiltrometer. Measures field saturated hydraulic conductivity. And we just have it shown schematically here, a device that sits on the soil surface, another device that controls it, and a source of water. Now, start out just by talking about what hydraulic conductivity is. It's a measure of the ability of a porous medium to transmit water. And to get a bit of a feeling for what that means, if we let I indicate the water flux, the amount of water per unit area per unit time, we can say that that's equal to K, a hydraulic conductivity, multiplied by the gradient in head, dH dz. The head gradient is the force causing water to move in soil, and the K is the proportionality factor between that driving force and the flux of water in the soil. We can expand the head out into its two main components. HM is the matrix head, and HG is the gravitational head. And so we have matrix forces causing water to move through soil and gravitational forces. Now, the matrix or the gravitational gradient, dHg dz, is just equal to 1. And initially, as we apply water to soil, matrix forces are pretty strong and draw water into the soil pretty rapidly. But if we let infiltration occur for a long, long time to where the soil's pretty wet, that gradient in matrix head goes to 0. And so at long times, the infiltration rate is roughly equal to the hydraulic conductivity. And that can give you some feeling for actually what the hydraulic conductivity means. If we were to apply water for a long time, that the rate at which the water would infiltrate into soil would be about equal to the hydraulic conductivity. A hydraulic soil can be either saturated or unsaturated, and so the hydraulic conductivity can be either saturated hydraulic conductivity or the unsaturated. In this graph, the vertical axis is at 0 head, and values to the right of that indicate saturated conductivity values. Values to the left indicate unsaturated values. And if we take the line on the right in the center, that would be maybe a value that you might find for a sandy soil. Now, one thing to point out is that that vertical axis is a logarithmic axis. Think of differences in that as order of magnitude differences, factors of 10, not factors of 1 or 2. And so if we look at, say, a poorly structured clay soil, the lower line, it would have a saturated conductivity quite a bit lower than the sandy soil would. On the other hand, if that clay soil had good structure, if there were aggregates and large pores between those aggregates, then its saturated hydraulic conductivity could be somewhat higher than the conductivity even of a sand. Now, if we go to the left side of the graph, where the head is negative, the water potential is negative, the soil starts to desaturate, the pores empty. And as the pores empty, especially as the large pores empty, the hydraulic conductivity decreases dramatically, and especially where there are large pores present. And so the unsaturated conductivity is always less than, and in most cases, much, much less, orders of magnitude less than it is when the soil is saturated. So what determines the hydraulic conductivity of soil? Well, we've just talked about two of those factors, the soil texture. Coarse textured soils have higher hydraulic conductivity than fine textured soils typically. And the soil structure, structured soil typically will have large pores present in it, and structureless soil, smaller pores. Biopores, root channels, or animal burrows can have a big effect on saturated hydraulic conductivity if they're filled with water, unless they come all the way to the surface so that they can fill with water, then they can actually decrease conductivity rather than increase it. And compaction, or the density of the soil, certainly will have a big effect on hydraulic conductivity. And then, as we've mentioned, the water content or the water potential of the soil is important. Now, why do we care about hydraulic conductivity? Well, it impacts almost everything that soils are used for. And so crop production has to do with how the water gets into the soil, how the water gets out of the soil, how the water flows to the roots of a crop. So has important impacts there. Irrigation and drainage related to how water gets into and out of soil. Hydrology, both urban and hydrology of native lands, and the water movement in soil, the water moving into and out of soil. Landfill performance, we design landfills to minimize the water movement out of the landfill, to minimize maybe or capture water before it flows in. We need to know the hydraulic conductivity to do those calculations. When we're designing stormwater systems, infiltration is an important thing. And even in applications like soil health, that a soil that has poor hydraulic properties is not a healthy soil. Well, let's talk a bit about methods for measuring hydraulic conductivity. Mentioned just quickly a couple of laboratory methods that are useful. These are used pretty often for characterizing soil hydraulic properties, but they require that we go to the field, take a soil core, try to take that in such a way that we disturb it minimally, and then bring that core back to the laboratory to make the measurement. Meter has a device that will measure the saturated conductivity of that core. Inside the blue part of this apparatus, you put a soil core that you've brought in from the field. You fill up the tube with water. You establish steady flow of water through that soil core, and you measure the rate of flow, and from that calculate the saturated conductivity. Another device that also is something that we build and sell here is called the high prop. Measures the unsaturated hydraulic properties of a sample of soil. Again, we go to the field, we get a soil core, we bring it back to the laboratory and put it on this device. The device has 2 tensiometers inside it to measure the soil suction. The water evaporates from the top of the soil column to establish a gradient within the column. We measure the rate of water loss from the column using the balance, and then from the rate of water loss and the measurements of tension, we're able to determine both the moisture release curve and an unsaturated hydraulic conductivity function for the soil. Very few methods exist for getting that unsaturated conductivity function, but this does it nicely. Now I've just put one of those curves that comes out of that here. It's the moisture release curve for a soil, Porous silt loam in this case. The volumetric water contents plotted on the vertical axis, and the logarithm, or the water potential or suction, is plotted on the horizontal axis as log scale. Now, I don't have a graph here that shows the unsaturated conductivity function, but we get similar detail to this with that function. Now, if we want to go to the field to make a measurement of hydraulic conductivity, we call that the field saturated hydraulic conductivity. We have several options. One option is this single ring infiltrometer. It's just a single cylinder that we drive into the soil. Can have various diameters, maybe from 10 to 50 centimeters, or sometimes even bigger than that. We can either maintain a constant water head in this and measure the water flow into it, or we can do it as a falling head method, let the head decrease as water infiltrates and measure that. It's pretty simple. There are some publications even that call this the beer can method. The water that flows out doesn't flow directly downward though, because there are matrix forces, so it flows both downward and laterally. And in an effort to try to deal with that and make the flow more one-dimensional, people have used a double ring infiltrometer as shown here. So there are 2 rings. The inner one is just like the one we just described. The idea of the outer one is that we maintain a head in that, the same as the head on the inner one, and that outer one is supposed to make the flow from the inner infiltrometer one-dimensional, so that it just goes down. I'm skeptical of that, but at least that's the idea of it. So one of our researchers here at Meter did his master's degree at Texas A&M University measuring hydraulic conductivity in a fairly large area that had been subjected to different kinds of land use. And the idea was to try to quantify the differences in hydraulic conductivity that resulted from the differences in land use. And the photograph here shows you the equipment that he had to set up to do that. You can see 3 of the double ring infiltrometers that he used here and 3 of the setups that he used to try to maintain a constant head. You can see that there's quite a bit more equipment that goes along with this. A pickup with a flatbed trailer and a large tank on it for hauling water. You can see where he's had to have some lawn chairs and some shades set up so that there's a place for them to get out of the sun while they're taking the measurements, and even a cooler sitting out there with not sure what's inside it. But anyway, a lot of equipment has to go along with this set of measurements. They made over 200 measurements of saturated conductivity, and measurement times took close to 2 hours a lot of times. And for that experiment, something over 2,000 liters of water. So you can see this is not a undertaking for the faint-hearted. He was able to show the things that he wanted to show with all that work, though. Well, we could think of this whole, think through the work that Leo had to go to accomplish this, and think maybe there are some other ways of doing that might work better. Some of the observations that would have come out of this is that hydraulic conductivity is spatially and temporally variable. Way more variable than we'd like it to be. It's hard to get enough measurements to really establish differences and to be able to model the kinds of things that go on in a field. The double ring infiltrometer takes a lot of time and a lot of water. It might occur to us when we were hauling all of that water that it might be possible to use mathematics to eliminate the need for that second ring. There probably was a time when we were limited enough in our mathematical capabilities that we would have needed to stick with just one dimension. But those times are long past, and there's no reason why we can't use mathematics to model flow from a single ring. It's hard to measure and control infiltration in head. It takes a lot of work, a lot of time to do it. Why not just do that electronically? And then finally, sorptivity is the flow that when you initially start an infiltration experiment, the water flows a lot faster than it does after a period of time. That's because the matrix forces are drawing water into the soil rapidly. And that has to be taken into account in order to get accurate measurements. Why don't we automate that too? And so the goals in designing the dual head infiltrometer were to fully automate the measurement and control, to reduce the water requirements, to make it portable. Portable meaning not needing a pickup and a flatbed trailer necessarily. We still needed to have a wide range of hydraulic conductivities that we could measure. We wanted to be able to characterize soil that would be used in lagoons, manure lagoons and other places like that, as well as soil that was well structured in a cultivated field. And we wanted to be able to automatically calculate the field saturated conductivity. Now, the equations that apply to this, we can start with the conductivity being equal to the water flux I divided by a function F, capital F. And that function takes into account both the sorptivity and the three-dimensional nature of the flow out of a single ring infiltrometer. And we won't go into the details of that. Those are given in a paper by John Nemo, published in 2009. But we can see that the equation that he came up with here, that F was 1 plus a set of variables. And so if that set of variables of lambda plus d go to 0, why then F goes to 1, and we get that equation we presented in the earlier slide, in the third slide, that the conductivity is equal to the infiltration rate. But those other factors take into account the three-dimensional nature. Now, lambda is a characteristic length of the porous medium, and we don't know what that length is necessarily, and so it will be nice if we can eliminate that from our measurements. D is the depth of ponding of the water on the soil surface, and then the small d and small b factors have to do with the insertion depth and the radius of the infiltrometer, and would combine those into the factor delta that's just a characteristic of the infiltrometer that we built. So if we were to make measurements at two ponding depths, we can write two equations in two unknowns, and from those two equations we can eliminate the lambda factor, which is the characteristic length of our porous medium, and so we get the hydraulic conductivity in terms of the two ponding depths that we have and the characteristics of the infiltrometer and the infiltration rates that we measure. So to give you an idea of how that analysis is done, I have on the left here the pressures that we establish, the two different pressures, and we do this in the past. That's been done by filling the ring to a greater depth or a lesser depth. But what we do is apply air pressure so that we can go quickly from one to the other, and so that we can do that automatically. And then on the right is the flux, and you can see the two infiltration values. We supply the water, control the water at a constant level, and supply water with a pump that can measure that infiltration rate. You can see the two depths that we have, and so we combine those to get the hydraulic conductivity. So we control the water level electronically. There's a level gauge inside that monitors that. We have a stepper motor that we can accurately measure and control the infiltration rate to maintain that level of water. And then we adjust the air pressure inside the chamber to get the two different heads that we use for infiltration to get the dual head calculation. We call this device the SATURO, and it provides an automated field saturated conductivity measurement. The measurements done automatically, that it's just set up and left in place, come back and get the result. We've vastly reduced the water requirements by both the algorithms that we use and the fact that we use a single ring infiltrometer. It's portable because of the reduced water requirements, and we can measure a broad range of infiltration rates and then just gives out the number that you want, the saturated conductivity. So got a couple of pictures here showing the installation process. Starts out with the ring that's pounded into the ground. You can see that on the left, and on the right is the ring installed and ready to go. Then the cap that's put on the top of the ring and sealed to it. There's an O-ring so that we can pressurize that chamber on the top, and so that the water level of about 10 centimeters can be established inside that. Tubes are hooked up to the control unit that's on the right. We set up the program that we want to run in the controller, then hook up the water supply that's just a collapsible plastic bottle, and you go off and leave it, and it sits there for a period of time, an hour or two, and makes the measurement that you want. You come back and it's all finished. You can see here the flux measurement over time. You can see that due to the sorptivity, the infiltration rate starts high and decreases over time, and then you can see the steps in that as the pressure is applied and the infiltration rate goes up, then the pressure goes off and the infiltration goes down. And so we have our two levels of infiltration, our two infiltration rates. And so here again, you can see the two values that it gets. So we did a little experiment just to compare the double ring infiltrometer with the dual head infiltrometer, the SATURO, and you can see the things that we used here. We did this experiment on we have a soccer field out behind our meter building. And so on the right here, you can see several locations where we made these measurements in that soccer field. And we compared the two methods at those locations. You can see here the results, the double ring results that we got and the SATURO results. And again, a pretty good agreement between the two. I mean, if you're not used to looking at saturated conductivity, field saturated conductivity data, these data may look a little bit noisy, but if you are used to that, you'll be amazed at how good those look, except for a couple of readings. You can see those were both on the bottom end of the field up against where the ground slopes up rapidly. And in those, the SATURO gave larger numbers than the double ring infiltrometer. Now, if we plot those, we can just comparing to a one-to-one line, except for those two, the comparison is a good one. So in general, we think that the double ring and the SATURO or dual head method compared well, except in those cases where flow was obviously dominated by large macropores. We think probably in the installation of the double ring that causes a lot more disturbance, and the macropores there were damaged as we did the installation. So I hope that gives you a feeling for how the SATURO works, how the dual head infiltrometer works, and gives you a feeling for opportunities where that can be applied to hydraulic conductivity measurements. Thank you.